welcome and thank you very much for joining. I'm Ellen Longmire from the CSE Dean's Office, where I'm Associate Dean for Academic Affairs. And I'm gonna try to moderate this competition and tell you a little about it before the contestants give their talks. This is part of a global competition. It was started by the University of Queensland in Australia. And we think our local competition is going to be really competitive and exciting. Please go to the next slide. Can we go to the next slide, Ray? Here we go. So here's an outline of our program. I'll first talk about the rules of the competition so everyone knows and what are the judging criteria. Then we'll have presentations, after which the presentations will be judged and we'll have a people's choice vote. We'll also have a question and answer session where anyone can ask questions about the content of the presentations. And finally, we will award the winners. Please go to the next. So what is 3MT? The idea behind it is we're asking students in 3 minutes to explain the gist of their research, the importance of their research in an engaging and easy to understand format. Please, next slide. And why are we doing this? To celebrate and show off some of the exciting research going on in our college, and also to cultivate and demonstrate students' presentation and communication skills. Next slide. We will be offering prizes for first prize as well as the runner-up. And we'll have a separate prize voted on by the audience called the People's Choice. Next slide. We do have judges for this competition and I'd like to introduce them. They're all illustrious alumni of our college. I'll start with Dr. Lynn Frostman. She's the Vice President of Engineering at Syzygy Plasmonics and a graduate of chemical engineering. Do you want to say hello, Lynn?
Sure. Hi, everyone. It's a pleasure to be here. I'm very much looking forward to seeing the presentations from the students.
Thanks. We also have Dave Knapp, Dr. Dave Knapp, who is the VP of Corporate Research at Boston Scientific, also a graduate of chemical engineering. Dave, would you like to say hello?
Absolutely. Hello, everybody. And it's just fantastic to be here. Can't wait to see the students' presentations.
Okay. And we also have Jane Lansing. She's the brand officer and VP of marketing at Emerson Automation Solutions, and she's a grad of civil engineering. Jane, can you please say hello?
Hello, and congratulations to all the students for just participating in this.
Thank you. So the judges, can we go to the next slide, please? Okay, first I need to state the rules of the competition, and that is students are allowed a single static PowerPoint slide. They have 3 minutes to present. There's a limitation that this should be spoken word only, no singing, rapping, no poems. And you'll see we'll start a clock with each speaker. So each speaker clearly has 3 minutes. And the judges will make the decisions on the winners. We will also have the separate people's judges doing the people's choice. Next slide, please. Okay, so you know, these are the judging criteria that are used. First of all, the judges are looking at comprehension and content of the presentation, including background and significance of the work, impact of the work, is the presentation clear and logical? Separately, they're looking at engagement and communication with the audience. Does the presenter make the audience want to know more? Convey enthusiasm for the research? Capture and maintain attention, and also have sufficient stage presence. And lastly, the slide that's shown, does it enhance the presentation? All right, so we will have 15 contestants in sequence. The winner will advance to the university-wide competition, which takes place on November 13th. That will include student representatives from all colleges across the university. Beyond that competition, the winner of that one is allowed to go to a national competition. So after the contestants are finished presenting, our judges are going to take a little time to deliberate and decide on the winners. And during that time, we'll have two activities. One being the audience will be allowed to vote for the People's Choice Award. And secondly, the audience can ask questions of any of the presenters if they'd like to know more about the work, for example. So next slide, please. All right, so now we're ready to start off. And the first contestant will be Jeffrey Bees. He's from mechanical engineering. And the title of his talk is Making Iron Man Suits Real.
Hello, everybody. I hope you enjoy my talk. Take a moment to imagine yourself or a loved one working long hours at a factory, risking injury from overexertion, or maybe running for miles carrying 100 pounds on your back while serving your country, or perhaps struggling every single day to regain your mobility after an accident. Situations like these account for millions of people in the US alone. Now, what if I told you that you could have the strength or endurance to get the job done, or simply that you could go for a walk with your family? From restoring mobility to enhancing capability, robotic exoskeletons are a beacon of hope for both the individual and society as a whole. Now, what do you think of when I say robotic exoskeleton? Perhaps you think Iron Man. Even without superpowers like flight or energy blasts, his suit has a lot of important features. It's a sleek design that is strong, flexible, form-fitting, gives him the energy he needs to get through the day, and even keeps him comfortable in extreme temperatures. We don't have Iron Man yet, but my research will lay the foundation to make it a reality. First, let's define some basics of a robotic suit. Looking to the left, the pipe uses high-pressure fluid to provide the necessary power and control. However, this can get really hot and become inefficient at a small scale. The metal beam provides the necessary support, but is also heavy, making it harder to move. My thesis will use generative design to address these challenges and create a single structure that is lightweight and cool to the touch, while providing the necessary power. Generative design is a big buzzword these days, and the basic idea is that it takes all the iterative guesswork out of designing a product that is then optimized for whatever task needs to be performed. First, you define environmental forces, temperatures, or flow rates, and then important goals like reducing weight or temperature. Then you click run and watch as the product evolves into being by adding, subtracting, and moving material, guided by lowering the stresses, temperatures, or pressures until it reaches a minimum shown in blue. Algorithms of prior research have reduced weight, increased cooling rate, or improved flow efficiency, which is exactly what we need. However, currently we can't have all three at the same time. My research combines these factors into a single algorithm to create the optimized design to the right, which will require the capabilities of metal 3D printing to make the very organic shape a reality. My preliminary work has already reduced weight by 88%. The success of my research will reach far beyond the field of robotics and extend to many areas of machine design. Thank you.
Thank you very much. Okay. So we'll go to the next speaker. The next speaker will be Joe Booch. He is from Aerospace Engineering and Mechanics. And the title of his presentation is, Will it be a hit or a miss?
Hello, everyone. Thank you, Alan. I'm ready. Will it be a hit or a miss? So missile defense has been one of the top priority for the US in last couple of years. And the threat environment is ever increasing with its own capabilities. For example, intercontinental ballistic missiles that are being developed by countries like North Korea, China, and Russia. And the threats can also be, for example, drones or unmanned vehicles that can take different trajectories to hit our assets. So here as an asset, I'm showing a ship, but it could be a city or it could be any other asset that we can think of. Now these threats can destroy our assets. So preventing these type of threat is crucial. And in order to prevent them, we launch interceptors. These interceptors try to hit the threat, and failure to hit the threat can result into dangerous consequences. For example, losing an asset or failure to prevent a nuclear strike or nuclear attack. So currently how this is done is we launch an interceptor. We know that certain dynamics, certain physics or mathematics that we can describe these type of engagements. But the threat environment itself is uncertain. There are external disturbances, for example, wind gusts that can push your interceptor far away from the threat and it would not hit your threat. So what we currently do is we simulate these type of different scenarios in a supercomputer, and we try to assess what is the probability or what is the likelihood that I'm going to hit my threat. If I'm not going to hit my threat, then I better be launching additional interceptors. And these type of decisions, you have a very short reaction time. You really don't have performing thousands of simulation to understand the probability of the intercept. Now, in my research, we are developing a theoretical and computational tools to assess the robustness or to assess the probability of the interceptor, whether it's gonna hit my threat or not. And so this research is being funded by the US Navy, and we collaborate with University of California at Berkeley. These type of analysis will help us to make a follow-up decisions, whether we want to launch a second interceptor or we want to save it to intercept it with other threats. Thank you for listening.
Thank you very much. Now we'll move to the next talk. This will be given by Lizzy Christ. She is from Biomedical Engineering, and her title is Understanding the Complexity, a new tool to study cancer spreading.
Great, thank you, Ellen. I'm ready. Hi, everyone. My name is Lizzy, and I am here today to inform you that there is no cure for cancer. Before you slam your computer shut because I just ruined your weekend, let me explain what I mean. The bottom line is that cancer is not a single disease. It is a collection of diseases that are highly dynamic and variable. When you think of cancer, you might think of a lump of cells. And while true, this definition is too simplistic. If we want to understand why cancer is so hard to treat, we must consider what makes up that lump of cells and how that lump is able to spread throughout a patient's body. In my opinion, a tumor is like a pasta dish. To create tumor pasta, you need noodles, which we call the extracellular matrix. This is the web that keeps everything held together. Within the noodles, we have the main player, meatballs, which we call our cancer cells. But meatballs and plain noodles alone would not be very good. And so fortunately, there are other ingredients or cell types in a tumor environment that make it tasty. And by that, I mean dangerous. These extra ingredients help support the tumor's growth and survival. And if you change the amount of them or add in something new, the dish will taste completely different. In our cancer analogy, this means that tumors look different from patient to patient. We call this variety heterogeneity, and it arises from differences in the genetic makeup of the cancer cells and the combinations of ingredients in the surrounding tumor environment. As a result of this heterogeneity, a subset of cancer cells will develop the ability to move around within their environment, enter the blood vessel system, which acts like a highway in our body, and circulate until exiting off the highway and taking residence in a new organ. This process of cancer spreading is called metastasis, and it is responsible for over 90% of cancer-related deaths. The consequence of tumor heterogeneity and cancer spreading is that a universal cancer cure is extremely challenging, if not impossible to develop. In fact, over 90% of anti-cancer drugs fail during clinical trials, which can take up to 7 years and billions of dollars to carry out. Despite significant progress in cancer research over the last few decades, an area that still needs innovation is the development of models or platforms to study cancer and test anti-cancer drugs. One critical limitation of existing models is that they do not fully replicate the complexity of cancer, meaning they do not consider the influence of different tumor ingredients. Additionally, existing models investigate either the early steps of metastasis or the later steps, but not the full process in sequence. To streamline cancer drug discovery, save millions of dollars and years of time, I created the first model of cancer progression that mimics both tumor heterogeneity, shown on the left, and the full process of cancer spreading, shown on the right. This model of metastasis will allow us to study how breast cancer cells go from a ball of tumor pasta to circulating in the bloodstream to eventually creating a new tumor in a secondary site. Using this platform, I'll be able to investigate how different ingredients contribute to the process of metastasis, which will allow us to identify new drug targets to stop the spread of cancer. With this information, we'll be one step closer to finding some of the cures, plural, for cancer.
Hello, everyone. Thanks for listening to my presentation. Alan, I'm ready.
Hang on. I'll introduce you.
Oh, sorry.
Thanks a lot. The next student is Aditya Dave from electrical engineering. The title of his work is A Plant in the Spotlight of an Antenna.
Yeah, I'm ready, Alan.
Thanks.
The UN estimates that we need to double our agricultural production within the next 30 years to feed the increasing population. That is a really short time span. Increasing the number of farms is not an option, since in the last 5 years alone, we have lost 2% of the farmlands in US. This clearly means that continuously monitoring the health of our plants is the only way to maximize our agricultural production and feed people. Water content is one of the chief indicators of health. Well-hydrated plants survive longer since they are less prone to diseases. They are also less likely to start wildfires, which can help us avoid these dreaded natural disasters that we witness every year. To preemptively take measures in case our plants lack water, my work involves developing antennas that can non-invasively measure the water content of plants. Typically, big antennas are used to communicate over large distances. For example, your TV dishes, which communicate with satellites. My antennas are around the size of your fists, but they perform just as well as the TV dishes. Let me tell you the secret sauce. It is placing a lens on top of the antenna. This lens performs the same function as eyeglasses. It focuses all the energy that is sent and received onto a small spot near the antenna, which allows the antenna to see better. This simply means that even though my antennas are small, they have a great resolution while measuring objects that are located far away, sort of like focusing a spotlight. We can mount these antennas on top of drones to study small areas more effectively. By small areas, I still mean squares of kilometers of your corn and wheat fields. Remember, less water makes our plants very sad. We can find out whether our plants are happy or sad by sending signals using my antenna. We study the responses of the signals that are reflected back from the plant and soil samples and measure the water content. Or rather, I should say, we can learn how the plants feel. Large-scale application of this technology has a great potential to preempt natural disasters like the wildfires and also improve our agricultural produce, both by monitoring the health of our plants. So let's for once give our environment some attention. Let us bring our plants into the spotlight. Thank you.
Thank you. Thank you very much. Our next talk will be given by Shuyin Dima from chemistry, and his title is Sponge Out Phosphate.
And ready. Phosphate is an essential nutrient and plays an important role in our daily life. Not only is phosphate widely used as a fertilizer to promote crop growth, but it's also a key component of teeth and bones. Despite the significance of phosphate, too much of it is problematic. The phosphorus fertilizer runoff into lakes or ponds causes eutrophication that further leads to algal bloom and affects the whole ecosystem. Abnormally high levels of phosphate in blood, a condition also known as hyperphosphatemia, can withdraw calcium from teeth and bones, promoting calcium deposition on soft tissues as shown on the bottom left, which is painful and often requires surgical removal. 65% of estuaries and coastal waters in the US have moderate to severe eutrophication, and almost all patients with dialysis-dependent kidney failure have experienced hyperphosphatemia. It is therefore critical to manage phosphate levels. Current methods are either inefficient or costly. Furthermore, most of the developed phosphate receptors do not work in water or lack selectivity for phosphate in the presence of interferences, which are the most important criterion for phosphate remediation. Our research has therefore been focusing on developing metal-based receptors that can sponge out phosphate. Our receptors have met the most important criterion. They function in water and are also selective for phosphate in the presence of interferences. They also feature tunable binding strength that allows us to customize remediation accordingly. By using a rare earth metal, such as europium, when the receptor binds phosphate, it becomes highly luminescent. This is ideal for monitoring the binding at low concentration and in complex media, because the emitted light specifically tells you the presence of phosphate, and is also very sensitive. Lastly, the process is reversible, meaning those receptors can be reused, and that ensures a sustainable phosphate remediation. However, due to the safety concern and cost of rare earth metals, we are transitioning to safer, more economical, and sustainable metal-based receptors. We have made the first and successful attempt to implement iron-based receptors for phosphate remediation, which have similar functions to europium-based receptors, but at a much lower cost and toxicity. In summary, this research provides an efficient and effective approach to sponge out phosphate by the use of metal-based receptors. Our ultimate goal is to build a prototype to clean up phosphate, though it might not be in the shape of a sponge. Thank you.
Thank you. All right. Our next talk will be given by Myun Jeene from chemistry. Title of her talk is From Intra to Inter. How?
Okay, I'm ready. Hi, everyone. Today I'm going to talk about my research topic from intramolecular to intermolecular. So for most of the organic chemists, they probably know that for a chemistry reaction to work, it usually involves two reactive sites to get access to each other, and they collide, and the reaction happens successfully. So for some types of particular organic reactions, the two sites are bound to each other by a covalent linkage, or something like we call chemical bonds. So they are physically attached to each other, which is considered to be an intramolecular reaction because it's considered one single molecule starting material. But it turns out that scientists found that if there's no linkage between the two reactive sites, when they are located on two separate molecules, the reaction does not go through because of the really high energy barrier that is calculated by computer. So imagine that a reaction is like climbing a mountain. If the mountain is not very high, the reaction can go through easily. But if the energy barrier is much higher, it needs harsher condition to make the reaction happen. So for example, you need to heat it up to like 300 degrees and wait for 3 months. That's really an inconvenience for organic chemists. So to make this transition from the intramolecular to intermolecular work, scientists have been devoting a lot of effort to it. So my idea is that I have been engaging what is so-called a Lewis pair interaction. So it's actually a magic invisible attraction between a Lewis acceptor and a Lewis donor due to the nature of the atoms. So it turns out that the donor will automatically find the acceptor when the two molecules are dissolved in an organic solution. So basically, it's like building a virtual bridge between the two molecules. So with that interaction present in this reaction, the two reactive sites has larger chance to meet each other and let the reaction happen. So my point is that by involving non-covalent interaction into the reaction, we lower this energy barrier by a fair amount. So make something that is impossible to possible. So with this, this is a very first report of intermolecular strategy that can save a lot of time for organic chemists, giving like less effort to a larger access to the target molecules. Thank you very much.
Thank you. Ready? Our next speaker is Daniel Kennedy from Civil Engineering. His title is, Just How Deep Are Those Piles Anyway?
Great, I'm ready to go. Okay, first of all, I want to say thank you to the Minnesota Department of Transportation for funding this project. I'm very, very grateful for that. My long title of my project is Detecting Pile Length of High Mass Light Tower Foundations. First I want to kind of go through what a high mass light tower is and kind of why are we interested in them. As you can see in the background, a high mass light tower is a tall, slender structure, typically 100 to 140 feet in height. We see them on freeways, intersections, or like the background picture suggests at shipping ports also. Because of their tall structure, they have high overturning forces generated at the base of the tower. And to overcome this, it has a unique foundation system, which can be seen on the left, which is 3 inclined piles connected to a pile cap. These foundations are typically 30 to 40 feet in depth. Now, Minnesota has 400 of these towers, over 400 of these towers, with 211 of these towers having no pile depth information associated with them. Without that pile depth associated with it, we're not able to recertify these towers with new structural design criteria at a cost of about $20,000 per tower replacement. If we come up with a successful testing method, it could save Minnesota over $4 million in unnecessary replacement costs. So I guess how are we going to test for these, right? So in the middle, I have kind of two methods that we've identified. We have a pneumatic shaker test and we have a hammer impact test. Both these tests use a cone penetration testing truck with seismic geophone to listen to the ground movement next to the pile. The first test is the shaker test. You can see this in the middle on the top image. We actually take a shaker and secure it to the top or to a steel rod in contact with the pile cap, hopefully directly over the pile. This then in turn shakes the pile on the ground. And then this is done at different depths next to the pile. We take that signal in time, use a Fourier transform to convert it to the frequency spectrum, and then that gives the amplitude of the ground motion at that testing depth. Method number 2 is the hammer impact test. This is done in conjunction with the shaker test. The hammer actually triggers our data collection software where we can listen for the first wave. This uses a wavelet transform to transform that time signal into the frequency components, which is seen on the y-axis. And then we can pick that first wave arrival out in time. So I guess the burning question is, how does this work, right? So on the right, I have 2 vertical plots. The left vertical plot, I'm plotting the results with the shaker test, or I'm actually plotting the magnitude of the ground motion with increasing depth. The right vertical plot is the results from the impact test. I'm plotting the wavelet transform at different depths there too. We see great correlation between the numerical modeling and what we see out in the field. Our plan is to take this data and put it into a machine learning type predictive software so we can take the data, put it in, get out the depths of these piles. But as you can see with the plots on the right, it's a good visual response around 32 to 34 feet deep. And the only reason for that would be the pile on the ground, which is what we're looking for in the first place. Thank you.
Thank you. Our next speaker will be Katherine Maxwell. She's from mathematics, and the title of her talk is Fuzzy Donuts and Flat Planes, Applications to String Theory.
Thank you. Thank you, Ellen. I'm ready. Have you ever heard that we live in a 10-dimensional universe? That is the prediction made by physicists studying string theory. That means in addition to the 3 spatial dimensions and the 1 time dimension, there are somehow 6 hidden dimensions. While I won't be able to explain the prediction of 10 dimensions today, I will explain how it is key to my research. You see, in string theory, physicists hypothesize that the most fundamental processes in the universe are actually moving strings. Precisely circles which trace out surfaces as they move in space. The details of these interactions correspond to surfaces of varying sizes and shapes. The surfaces are in fact donuts with perhaps many holes, not just the familiar single hole. So imagine the space of all possible donuts of any size and shape and any number of holes. This space is very curvy and large. Physicists would love to be able to do particle physics computations in superstring theory. But to do this, they need to calculate integrals over the space of all donuts. That is, sum up numbers associated with each donut. There is, in fact, a complication to this I haven't explained yet. The super in superstring theory means that we require fuzzy donuts. This is not a physical fuzz. It is, in fact, too small to even see. The problem is then that the space of all fuzzy donuts, it itself is fuzzy. You may think that this is not a problem. After all, you can't even see the fuzz. But in fact, the fuzz on the space of donuts is tangled. To overcome this, my research proposes that instead of considering the space of all possible fuzzy donuts, we consider a collection of flat planes. Someone before myself figured out that for every fuzzy donut, there is a flat plane which represents the donut. The collection of these flat planes is roughly the picture on the right. My research is justifying how the integrals physicists want to calculate can be computed using this collection. The study of flat planes and lines is called linear algebra. And here computations are much easier. This is the goal. But we need justification that this is appropriate. You see, the number 10 is crucial to the integrals physicists want to compute over the space of fuzzy donuts. And the justification is that these flat planes can be used because the number 10 somewhat surprisingly shows up when studying these flat planes. My research has taken steps to rewrite the integrals over the space of fuzzy donuts in terms of the collection of flat planes. And this idea has potential not only to open the door to new predictions in superstring theory, but make beautiful connections in mathematics.
Thank you very much. We'll go to the next talk. The next talk will be given by Fernando Medina from Earth Sciences. And the title of his talk is, "Are You My Eukaryotic Ancestor?"
Thanks, Ellen. I'm ready. Thanks, I'm ready. A year ago, I came across this news headline that says, "Lost Jackson Pollock painting found in a garage could be worth 50 million." And when I saw the painting here to the left, while in my free time trying not to think about my thesis, I thought, oh my God, this is my $50 million thesis question. I was so impressed by the similarity of these coiled brushstrokes to one of the first fossils of possible eukaryotic life that we know of. To the right, there is a picture of a rock containing such a fossil called Grapenia spiralis, dating back 1.9 billion years, which could be one of the earliest forms of complex life that then diversified into plants, animals, and humans, forming a complete different domain of life that we now call eukaryotes. So these coils here maybe our oldest ancestors. The emergence of this creature, the reason we are talking today. Unfortunately, we are not really sure if this is a eukaryote. We simply assume that based on its shape and big size relative to bacteria. An alternative that I'm exploring is to study preserved molecules contained in fossils. Turns out that besides the body fossil itself, molecules also get fossilized, and some of them are lipids that only eukaryotes synthesize. An example of that is cholesterol, a lipid that would be indicative of eukaryote. Unfortunately, the technique we have available today to study those lipids requires crashing down these rocks and mixing up all its components. So that will be the equivalent of tearing down this painting and then trying to identify a single brushstroke out of the mix-up colors and elements of the composition. Though I know the painting is already mixed up. But that's how the geological record is. It's already complex, so it just doesn't make sense to make it more complex. We're borrowing a technique from the biological sciences and applying that to rocks instead, where we can use a specifically designed molecule to track down certain lipids, aiming to look for particular cholesterol-like signals preserved in these presumably early eukaryotes. So that way we don't have to crash down this rock and lose our rocks. So we haven't gotten to that point, but our research suggests that we can fine-tune this technique and apply it to these rocks. So in the same way, this Pollock painting was discovered and rediscovered after decades, we can, for the first time, based on molecular evidence, rediscover our if these early eukaryotes are.
Thank you very much. So we have to move to the next speaker. The speaker is Bito Shra from computer science. His title is Epidemiology-Inspired Model for Fake News Spreading.
Alan, I'm ready. Social networks like Facebook, Twitter, and WhatsApp are used by millions around the world to not just share information, but also personal opinions about it, which is usually unverified. And unfortunately, this has caused the problem of fake news spreading in social media. Now, a lot of research has been done over the past decade to prevent fake news spreading, which have relied on trying to identify if the information is false or not. But my thesis tries to propose a complementary idea to this, where I try to identify whether a person is likely to become the spreader of the fake news or not. And my research is inspired from infection epidemiology. Now, in these COVID times, as you all know, epidemiology is the study of incidence, distribution, and control of infection in population. So my research is trying to map these ideas from infection epidemiology in the context of fake news epidemiology. So the idea of infection is analogous to fake news. Idea of population is analogous to peoples and communities in a social network. And the idea of medicine or cure is analogous to a refutation information, which is basically a news that fact checks the false information. So as part of my thesis, I've tried to propose 4 sequential phases. The first phase, called vulnerability assessment, deals with a scenario where the infection has not yet been introduced into the social media platform. So there you try to basically quantify the immunity of specific people and communities. And for that purpose, in the context of fake news epidemiology, I have tried to propose metrics to quantify the vulnerability of nodes and communities. Once the infection gets introduced into the system, phase 2 and phase 3 basically deals with the scenario where the infection has spread or is in the process of spreading, and we want to identify the spreaders or the likely spreaders of the information. Now, after the fake news is identified and its refutation gets created and is introduced into the social media platform, we want to control and prevent the spread of fake news by identifying specific nodes in the social media platform, which are more likely to spread the refutation information, and in this process, mitigate the further spread of fake news. Now, to try and sum up my entire thesis in one research question, so does trust between people act as a conduit for fake news spreading? And yes, through metrics that were inspired from the domain of machine learning, we did show that fake news spreading is more sensitive to trust than true news spreading. Thank you.
Thank you. Our next speaker will be Saira Ruia from computer science. The title of her talk is Human Machine Team Can Save Lives.
Thank you, Ellen. I am ready to go. Do you know that alcoholism is the 3rd leading preventable cause of death in the United States? Every year, more than 95,000 people die of alcohol abuse, and it costs the US about $300 billion US. So among many different recovery options, Alcoholics Anonymous, or A, is very popular with over 2 million members. So A hosts weekly meetings where people can gather, they talk about their problem, and they get a lot of support from others. However, my initial research shows that it is sometimes people find it very hard to get to these meetings because A prefers regional autonomy and it does not maintain a centralized list where you can search for meetings. Now, think of someone who just got out of a rehab, craves for an alcohol, and he decides to go to a meeting. So quick Google search shows him a meeting nearby, he drives down the road, and the meeting is not there. That is really frustrating, right? And that can even cause a relapse. So I'm trying to address this important problem by creating a countrywide AA meeting list. And that can also contain up-to-date information. So I'm a computer science researcher, so I thought, well, let's automate this whole process of collecting the meeting schedules. So I applied machine learning and pattern detection to develop a technique that can filter different web pages which may contain meetings, and then it can extract the time and location information for each of the individual meetings. But whenever things go out of pattern, computers can be really dumb, and it can fail to extract meaningful information out of those things. So for me, the problem was these meetings were in different structures and formats, like Google Map, somewhere on calendar, somewhere just scanned images. So this automated process actually confused an office hour or even a picnic with an actual A meeting, because those events also have time and address information. So that's why combining human intelligence was crucial. So I used crowdsourcing. That means I recruited online workers who could see this information that were extracted automatically, and they could validate and modify that information for us in exchange of money. So humans may not be able to solve thousands of equations in seconds, but it's very easy for them to differentiate a picnic from a meeting, right? So then I also sought help from community volunteers who are always willing to help out the newcomers. And finally, I tested this human in the loop technique to So I applied this human in the loop technique to extract meetings from 3 different states, Minnesota, Illinois, and Wisconsin. And I could gather accurate information for about 1,892 meetings, which are 95% of the meetings that were listed for those 3 different states. So yes, human machine team can save lives by enhancing access to support for recovery from alcoholism. And I think there is a lot of potential for this human integrated machine learning techniques to apply in other contexts as well. Thank you for listening. That's all from me.
Thank you. I'm sorry, I think we had a little glitch there. And I guess I want to ask, do we think we're okay?
Yeah, it's fine, I guess.
Fine now. Thank you very much.
Sorry, Annalyn, just give me a little, let me get a little bit of time here.
Okay. Whoops. Must be Zoom overload.
Go ahead, Ellen.
Okay. Think you're okay with the timer? I guess. Oh. Oh. Does it help if people not speaking turn off their video? I don't know.
Yes, if you have already gone, please turn off your video.
So thanks for hanging on, everyone. I think it looks good. Are you ready? Okay. All right. Thanks for hanging on, everyone. Our next talk will be given by Sagar Tamang from Civil Engineering. And his title is Accurate Weather Forecasting. Is the problem too flat?
Thanks, Aaron. I'm ready to go. Just last month, I went to northern Minnesota to observe the beautiful fall weather. But to my disappointment, what was forecasted as a bright sunny afternoon turned out to be a dull rainy day. I believe this is something that all of us have experienced at a certain point in our life, where the weather forecasts are so inaccurate, we start believing we don't need them at all. But the inaccurate weather forecast that caused me mild discomfort in extreme cases claims lives of thousands of people and destroys billions of dollars worth of properties. So weather forecasts are important, but how are these forecasts made? And why are they so inaccurate time and again? For any kind of weather forecasting, there are two major ingredients. First is the satellite data that's coming from a group of satellites orbiting around the Earth and sending us information multiple times in a day. So we take this data and feed it to the next ingredient, which are the powerful supercomputers capable of running hundreds of simulations at a time. So the task of a weather forecaster is to find the best possible way of combining these two pieces of information together to produce accurate weather forecast. The thing to keep in mind, though, is that neither the satellite data nor the simulations are accurate in themselves, but their powerful combination has the capacity to produce accurate weather forecast. So you might be wondering, everything sounds so simple. Where's the problem? The problem actually lies in the oversimplification of the problem itself. For so long, weather forecasters have been assuming that in an imaginary space where the problem lives is a flat surface. So in some sense, they are kind of like the flatter society, but for the weather forecasters. So when you do assume it to be flat, you can take satellite data and simulations as 2 points on that flat surface, connect them through a straight line, and just take anywhere in the middle and use that for simulations. And here lies the actual problem. During my PhD research, I found that the imaginary space that the weather forecasters have so long been assuming to be flat is not flat at all. It's actually a very curved space and behaves more like the surface of the Earth. So when you are falsely assuming it to be a flat surface, you're disrespecting the geometry of the problem. And that's why when you try to combine the information in the form of shapes that have a single high peak, you come up with these weird shapes that have multiple high points. But when I try to combine this information by the method that I've developed during my PhD, I preserve the geometry, I preserve the shape, and that's the reason the accuracy is really high. The large scale implementation of my research has tremendous potential to improve the weather forecast and will ensure that inaccurate weather forecast never gets to ruin anybody else's life ever again. Thank you.
Thank you. All right, our next presentation will be given by Daniel Thomas from Mechanical Engineering. The title of his presentation is Green Ammonia Fuel.
Thank you, and I'm ready anytime. So one of the exciting engineering stories of my lifetime is our progress in replacing fossil fuels with renewable energy. But we're still not close to kicking our oil habit. Last time you filled up your car at the gas station, you demonstrated one reason why. Gasoline packs a lot of energy. You put in a few gallons and you're good to go for another 400 miles. Now, electric vehicles are starting to get that kind of range with expensive battery packs. But as you can see in my bar chart, the energy density of an advanced lithium-ion battery is still just a tiny fraction of gasoline, 35 times less energy per gallon. That's why batteries just aren't practical for a lot of the oil uses. Take ocean-going ships or airplanes or crop drying for a few examples. Now, hydrogen has also attracted a lot of attention as a potential green carbon-free fuel, but hydrogen is hard to store and has a low energy density, even when stored at a liquid at minus 423 Fahrenheit. But if this hydrogen is reacted with nitrogen to make ammonia, it can be stored as a liquid at low pressure, just like propane. Green solar or wind energy can be used to separate nitrogen from air and hydrogen from water, and then combine them to form ammonia, as you can see in my flow chart. The resulting green ammonia could be used on demand as a carbon-free renewable fuel. Now, ammonia has a decent energy density and is easy to store, so what's the catch? To release the energy, you need to burn it, and pure ammonia doesn't burn well. It's hard to light and tends to leave lots of smelly unburned ammonia and nitrogen oxide pollutants in the exhaust. So in my research, I'm looking at burning ammonia with a small fraction broken back down to hydrogen. Ammonia-hydrogen mixture burns easily, and the main challenge with burning it cleanly is that we still don't fully understand the chemical reactions involved in the burning. I'm using laser-induced fluorescence to measure the concentration of particular molecules in the flame. To get the picture on my slide, I used a laser tuned to the right wavelength to excite hydroxide molecules, and then a camera to capture the energy released by those molecules, that is their fluorescence. I compared this to computer simulations to better understand the chemical reactions in the flame that produce the nitrogen oxide pollutants. As we better understand how ammonia-hydrogen fuel burns, this will pave the way for the use of green ammonia in many applications that are so far exclusively fossil fuel fired. And maybe within my lifetime, we'll finally kick our oil habit. Thank you.
Thank you.
Sorry.
I'll introduce you. Our next talk will be given by Lizzy Christ. She's in the biomedical engineering department, and the title of her talk is Plotting a Landscape for Cell Transformation.
Thank you. I'm ready to go. Okay, so life starts with a single cell. That single cell then divides into 2 to 4 to 8, then an embryo, then a body of all cell types that have different shapes and functions. This process is called differentiation. Researchers now can turn mature cells back to stem cells. This provides a great cell source for therapeutic use, because that means now you can take your own skin cell, turn them back to stem cell, and then differentiate them to replace your diseased heart cell or damaged skin cells. Moreover, it is also possible to convert one cell type directly to another mature cell type, for example, skin cell to heart cell, without bypassing the stem cell state. In short, researchers are developing many strategies to achieve their desired target cell type. Some of them are very close to success. However, many common problems occur. For example, many protocols produce multiple cell types other than the desired one. Some other protocols may not reach a final mature state, rather they stopped at an intermediate step. Therefore, we want to find a quantitative way to describe the cell transformation process so that we can identify obstacles during the conversion and know how far our engineered cell is away from the desired target cell type. So the figure on the left is a landscape metaphor for cell transformation. Basically, it states that cell differentiation is like rolling a ball down the hill. Stem cell at high potential will flow towards positions with low potential through different paths and end up in different phases. The valleys are the local minimum of the potential. They're relatively stable states of the cell. The figure on the right is our modeling of a heart cell differentiation. So we start with the stem cell, we add in proteins under certain conditions, and we achieve a cell type that is highly similar to heart cell. Taking the data from this process, we first determine how many cell identities we found. And then we measure the probability of cell belonging to each identity. That gave us how many valleys we have on the landscape, and also the location and size of the valleys. The height of the landscape is the stemness of the cell. We hypothesize that stemness is proportional to the number of signaling pathways that's being activated in each cell. Combining the two, we have this landscape. So that for this specific transformation, we can see it requires little activation energy to kick off the differentiation. But then there are two cell types that's being formed at the end, red and green. So we might want to block one path to improve this protocol. So moving forward with our landscape model, we hope to include more transformation and experimentally test the strategies. In short, we build a landscape model that provide information on cell stability and also optimization strategies that can be used for cell engineering. Thank you.
Thank you. Now we'll go to the next talk. This talk will be given by Yali Zhang from Electrical Engineering. The title of her talk is Nanometer-Sized Interconnect, Joints in Future Communication Circuits.
I'm ready, thank you. Hi guys, did you know there are 206 bones, but only 78 joints in your body? Each joint is very important. They are used to link bones while reducing the friction of motion. Similarly, the electronic interconnect plays a very important role in communication system. It provides transitions and connections for signal routing and system grounding. Just like joints, interconnect links different parts of a communication system while reducing the friction of signal movement. Of 5G and 6G application make their signal level very low. So the conventional interconnect with high loss are ineffective. Can you run faster with stiff knees? The answer is no. My name is Yali Zhang. Let me tell you how we build a better electronic joint for future communication system, which requires lower power consumption and a faster operation speed. We propose to use bundles of nanowires to form one low-loss interconnect in communication integrated circuits. Each of these nanowires are extremely small, almost 1/300,000 diameter of one single human hair. The good thing is this extremely small size makes the high-frequency signal easily to penetrate. Also, by bundling them together, the uniformity can be guaranteed and the total signal loss can be reduced. One important question that needs to be answered is how to determine the actual loss of these nanowires. Their size are small, so their associated signal level is low. To answer this question, my circuits are designed to magnify the signal level of these nanowires. Similar to a doctor who uses a stethoscope to check our tiny heartbeat sound. My circuit includes 30 interconnect building blocks, and each block includes 200,000 nanowires to increase the total signal level. Furthermore, the novel calibration circuits are designed to remove the influence from other signaling parts. So these nanometer-sized interconnect could be a game changer to future communication devices. Someday, if you are enjoying the enhanced digital experience, please remember, these little joints may be supporting the system. Thank you.
Thank you. So that was our last talk. I'd really like to thank everyone. I thought I really learned a lot, and really a sign there's a lot of interesting and outstanding research going on in our college. And what we're going to do now is our judges are going to confer about their rankings. And what you see is all of our contestants. You can vote for them for the People's Choice Award by going to the Z link that's posted. Should be available to anyone in the audience. So please try that. And at the same time, if you'd like to ask questions of anyone that you see depicted here, please, you can ask your question in the Q&A. And any one of these people can answer. So I'm looking for the questions. And I'd like you to know that I'm not voting in this competition in order not to introduce any bias. And I noted during this competition that we had about 117 participants, which is really great in terms of our audience. And the second thing is the panelists can ask one another if they have questions, because I think you can ask directly.
I think that there was a Peter who raised their hand for a moment. There are a couple other hand raises popping up and dropping down.
Okay. Can you put your question into the Q&A? So far I can't see any. Okay, here we go. I have a question for Dan, and I think that is Dan T. Any toxicity problems with the nitrogen-based fuel?
Yeah, thank you for the question. Yeah, that's a big deal with burning ammonia. Is any unburned ammonia is a big concern. So if you get ammonia in the exhaust, the level of ammonia that's allowed for safety reasons is 25 parts per million. So that's something that we're monitoring, and that's part of the challenge, is not just reducing the nitrogen oxide pollutants, but also the unburned ammonia. Thanks for the question.
Okay, thank you very much. I'm looking for other questions. Now we have a question for Dan K.
Sure.
But I don't have the question yet. So there's a question for Maureen, but maybe I'm just getting a thumbs up there. So far, I don't have your question. Here's another question for Katherine. What kinds of problems can we solve if we know more about string theory and the 10 dimensions?
So that's actually a question for a physicist. I'm a mathematician. But I believe it's the idea that right now the physicists use what's called the standard model. And they already know there's some problems with the standard model. It doesn't quite, their calculations don't quite match what they're seeing. And so they want to understand a model that matches what they're seeing better. From a mathematics perspective, it opens up tons of things between algebra and geometry and studying these very large spaces that I was talking about.
Thank you. Okay, so now I have Maureen's question for Dan K. And the question is, how will you do ground truthing?
I'd have to assume that I'm not quite exactly sure what's meant by ground truthing, but I'm assuming that maybe doing modeling is what's being asked versus the actual data that we're getting from the field. If I assume that to be the question.
Or how will you validate your data?
Yes, exactly. So that's yes. So we are that was something that I couldn't get into. I did have at the top of my screen, we had a little insert there for the Minnesota Supercomputing Institute. If I had time, I would talk about that too, but we are using the Minnesota Supercomputing Institute to do numerical modeling of the problem at different depths, different soil profiles, water, no water, different soil types, to mimic both of the methods that I have, the impact test and the shaker test. And so when I talk about correlation between the numerical modeling and what we're getting from the field, all I was able to show was from the field because I just have one slide. But we are doing that through the Minnesota Supercomputing Institute.
Thanks.
I hope that answers it. Yeah.
Thanks. So now I have a question about fake news. What leads you to believe that there are epidemiological similarities with social behaviors?
Yeah, thanks for the question. Well, when I say similarities, I won't say that there are like exact similarities with the phenomena, but what I'm trying to mean is that we can draw analogies between the idea that infection in epidemiology is something that people want to contain. And in the similar context, fake news is kind of an infection that as social media companies and even general people would want it to be contained and not spread beyond a certain limit. So that's basically the similarity on which like the entire research agenda is based on.
Okay, thanks. And I have a follow-up question for you. And the question is, in order to eliminate misinformation, don't you have to know the truth yourself in order to introduce a correction?
Yeah, that's a very good question. So in order to know the truth, I rely mostly on the fact-checking websites. So the phenomena that I have observed in my research, especially on the Twitter platform, is that even when the refutation gets created and it is confirmed that the information is false, the false information still continues to propagate. And that could be attributed to the fact that the people who are spreading the information, even after the refutation gets introduced, are maybe people who are not yet aware that the particular information is false. So that kind of answers the question that in spite of knowing the truth that an information is false, the false information can still continue to propagate for many days.
Thanks. Now I have a question for Sagar. You mentioned that your results are much more accurate. Could you talk more about the results you have achieved?
Yeah, so what we do is we run it on a model and we compare it to the ground truth. And we look at different statistics like statistical measure like mean squared error or even bias. And we found that this method of combining it on the curved surface or manifold actually, it improves the bias by around 80 to 90% than the conventional method that we have employed in the prediction centers throughout the United States. So that's something really I'm looking forward to.
So does that help us extend the time forward we can look?
Yeah, definitely. So what happens is whenever you are forecasting, the error builds up on time, right? So if I'm improving the error, the same forecast, but I'm improving a 90%, the same thing, I can do it over and over, but basically we look at certain threshold. So I want at least 50% accuracy, then you can definitely increase the forecast time period. So instead of 3 days, I can expect same accuracy, but for 7 days by my method.
Thanks.
Yes.
Here's a question for Aditya. Can you please explain how you can measure the water content in the plants?
Yeah, certainly. Thank you for the question. So this is usually done in like 3 phases. So first, we pick up the species of the plants that we are interested in, and we fully hydrate it. So that species of plants will be planted in a particular area, and we will be sending RF signals through our drones and seeing how much of the signal is being absorbed by the soil and the plant and how much is being reflected back. Then we'll do the same for a completely dry plant samples. And then by doing that, we achieve sort of an upper bound and the lower bound. And based on that, we can predict the water content of the intermediate plants, which have intermediate values of water content. So sort of in the end, we get like a heat map, which kind of tells us which areas in this particular subspecies have a greater water moisture content or small amount of moisture content, and then we can predict what areas need attention. So thank you.
Thank you. Here's one more weather question. How far are you from making this public so our meteorologists can get some help?
Yeah, so I've been developing it for a very chaotic model which mimics the weather systems. But always whenever we design certain algorithm, one of the things you need to keep in mind for at least for weather forecasting is how large and how fast it can solve it. Because the weather systems are very large, right? So you want a very efficient algorithm. So I'm currently reducing the computational time, and I hopefully will finish it before the end of my PhD. And I've put the papers in archive, and I'm planning to put it on GitHub to the course. So hopefully you can look at it later.
Thank you. So I have a question for Shuyin about the phosphate receptors. And my question is, so you're developing these new receptors, and if you were to employ those in an environmental context, do you need huge amounts?
So currently we are evaluating how to immobilize them onto solid support, and each receptor can bind up to 3 equivalents of phosphate. And we also transition to more affordable metals. So even though we might need a lot, it would be more economical to transition from rare earth metal-based to iron-based receptors.
Okay, thanks. Here's a question for Sabirat. What other areas do you think this machine-human team, intelligence team idea can be applied?
So I think this idea has potential to be applied in other critical contexts. So for example, let's say we try to help the people who have autism, and we try to prepare, we try to answer some questions they might have to cope up with their real life. So machine might not be able to understand fully the question in the context, then we can actually seek help from a crowd or even other autistic people who have similar problems to answer better their questions. So that's one example.
So when you use the kind of the crowdsourcing, is the strategy that you just make your listing public and ask people to improve it?
So currently I have used an online crowdsourcing platform, Amazon Mechanical Turk. So there we have in exchange of money, I create by chunks of tasks for them to complete. I show the meetings that I extracted with machine learning and pattern detection, right? And then they also see the actual website that the meeting was extracted from, and they match the information and then say, okay, this is the correct information. And also if that's wrong, they just modify the address or whatever, the time or the day of the time. And then, as I say, to reduce the cost of crowdsourcing, because it will cost a lot of money, if I have to update the meeting information periodically. So I actually, there are many volunteers who are always willing to help out the newcomers. They do service work, right? So this can be a service work for them. So I can actually utilize them to, do the data validation for us.
Thanks. Now here I have a question for Lizzy. Ooh. Sorry. Can you explain how your metastasis model can study both primary and secondary metastasis?
Yeah, thanks for the question. So my model has basically two chambers that are connected by a blood vessel circulatory system. And in the first chamber, the primary site, I put a tumor that is embedded in like a tissue, like a breast tissue. And those cancer cells can then migrate within that tumor chamber and get into the blood vessel and circulate, and eventually downstream get out of that blood vessel and start creating a new tumor in that secondary site. So it's basically just connecting two tumors with a channel that acts like a blood vessel. So you can look at both independently of each other and tune different parameters to see how it affects that process of metastasis.
So is the goal of the model, so you have this, it's kind of a comprehensive model, and it has tunable parameters. Is the goal to sort of then tune parameters to see the possible outcomes, or is it to try to match the parameters directly to data?
Yeah, I guess it could be both and. So the nice thing about models that are not, mice or in the body, you can actually change one parameter and see how it affects the process. So I would be looking at the, different tumor pasta ingredients, like looking at different cell types that might make metastasis happen more often. Or I would look at different parameters that would stop metastasis from happening, because that might inform some therapeutic target. But then, yeah, like if in theory the model replicates what happens in a human, you could, in theory, take a tumor biopsy from a patient, put it in my model, and test different anti-cancer drugs against it to know what might work for that patient.
Thanks. All right, here's a question for Jeffrey, who's been hanging around a long time since he went first. Is your work going to first lead to better prosthetics before becoming a full-fledged suit, or will you achieve a full Iron Man suit by the time you finish your PhD?
Oh gosh, that would be awesome if I could. Yeah, so actually it will start out with prosthetics. At this stage, our lab is actually working with kids who struggle with walking. And we've got setups that hook on to particularly the leg, knee, ankle area to try and help restore the capabilities of walking. So as much as I would love to come out of this with the Iron Man suit, it will start bit by bit, but it's a good feel good to know that it works with kids right now, helping them move.
I'm losing my connection. Okay, if you aren't speaking, please turn your video off. Thank you. Okay, thanks. I think I almost lost it there. Yeah, okay. So here's a question for Z. And the question is, you're sort of setting up this potential type model for moving from stem cell into a differentiated cell, type of cell. And what I remember in your slide is that stem cell could differentiate into different cell types. You talked more about heart cells, I think, but if you want it to become a certain cell type, how do you encourage that? Like moving toward a certain valley in the potential?
So you can determine the path you want to go to by adding different set of transcription factors, that is just proteins. And for example, adding retinoic acid, you can maybe turn it to keratinocyte, skin cell, or you add some BA to turn it to a nerve cell. So adding in different transcription factors, and also the conditions is also very important, like what type of gel that you grow your cell on. So basically it's just controlling the chemical environment and physical environment that cells stay in, the stem cells stay in, and you can turn stem cells to drive them to different sulfate. So what the model is able to predict is what are the key proteins that might drive one cell type to a specific direction. I hope that answers your question.
Can you hear me?
Yes, we can, Ellen.
Sorry, I was thrown off of. Okay. So our judges are back and being patient with the Zoom issues. Now I'm struggling a little with my, here we go. All right, so our judges are back. I'm sure it was very challenging, and I'd like to announce the winners. So I'm going to first say the first place winner, as determined by our judges, is Yali Zhang. Congratulations.
Oh, thank you.
And our runner-up is Sagar Tamang. Congratulations.
Thank you.
Each of you will be awarded $100, but really, we're very impressed with your presentation and your work. And we also have the People's Choice winner, and the People's Choice winner is Aditya. Congratulations.
Thank you.
Thank you very much. And yeah, the winner, please, you can turn on your video. And so people can see you one more time, including our judges. Great presentations. And Yali, we wish you well in advancing to the university competition.
Okay.
This was already a really tough competition with a lot of great candidates and contestants. And so I think you should be really well prepared, and I think you should have a really great chance at winning the whole thing. So
Thank you. I'm
I'd like
very,
to
yeah, very
encourage
excited too.
people in our audience and other contestants to attend that next level, which will be on November 13th at 10 a.m. I'd also, and you can look at that link to get the details. I'd also really like to thank all of our contestants for great presentations of your work. It's very impressive. Your presentations themselves were also very impressive. And it was really fun for me. I'm sure it was true also for our judges and those in the audience to learn about all these new topics. And I think the work is really outstanding and so interesting in so many different areas.
Ellen, if you
Any
wouldn't mind.
comment from judges?
Yeah, I wanted to jump in just to first off to say, you all are amazing. That was really outstanding. And you probably don't realize just how valuable of a skill set this is to be able to take something that complex and condense it down to 3 minutes and be able to teach it to somebody who isn't an expert in what you're doing. You're going to use that over and over again in your career. So we were talking about that as the judges. It's one of the hardest things to do. So really, really impressed and great to thank you for sharing your work with all of us.
Yes, thanks everyone. I'm really sorry we were limited a little on the bandwidth. I wish everyone were visible. And I'd like to thank the judges one more time. Ray Johnson, who set this all up for us, and I know it's a big challenge. You did a great job. I'd also like to thank Jill Johnson, who communicated with everyone and organized everything that happened today. So hope to see you all in a real form sometime in the near future, if possible. And for all the students, I wish you the best of luck on completing your theses and moving to the next level.